shared key, which is a symmetric key for secure network communications. We will also talk about email security and privacy issues and social issues. So, about shared keys, the reason we need shared or symmetric key is because public key cryptography is pretty expensive. So when we have two keys, public and private, then what happens is the public key is public, which means everybody has access to it. So if someone wants to talk to Alice, then they need to obtain the public key for Alice. And this key is on her website, so anyone can get it, or she can send it to them. So once they have that, they would encrypt the message using her public key. And the way this message is encrypted is by using an encryption algorithm, which is typically a one-way function, which means that it's easy to perform the function in one direction, which means it is to encrypt it, but it's difficult to reverse it. So it is difficult to reverse it, and it's impossible to use the public key to decrypt the message and obtain the plaintext. So we have encryption algorithm that is using public key of Alice to encrypt the message, and then in order to decrypt this message, the only way to do that is to use the private key. Now, this private key is private because this key was generated on Alice's computer, and it never left the computer, and it's never sent through the network. So from network point of view, this key is secure because nobody can see it on the network because it's never sent through the network. So Alice is the only person who has access to that key because that key is on her computer, and it's nowhere else to be found. So she would use a private key to decrypt the message. And would obtain the plaintext. This is called the public key cryptography. Now this is great, it's pretty strong. However, it's kind of expensive. So in order to find a balance between cost and security, we use a combination of public and private key in order to establish a secure channel, and then use what's called a session key, which is a shared secret key that is symmetric, which means the same key can be used to encrypt and decrypt the communication. And this is done for performance purposes in terms of network performance, because this is very slow and takes a long time, but this can be done quickly. So with shared key, the way it works is we would have A and B would be Alice and Bob. So some notations. R is a nonsense, which is R stands for random number. So Alice, for example, can pick some random number and use it as a challenge. Bob can do the same thing when establishing the secure channel. The key K would be key for Alice, for example. So if the key it says AB, this is a shared key between Alice and Bob. So what we have on the screen, the way this works is first Alice, if she wants to communicate to Bob through a shared key, first thing she needs to do is send her identity to Bob. In other words, she says, hello, I'm Alice and I want to talk to you. In response, Bob sends a challenge because he needs to verify this is truly is Alice. So he picks up some random number. This can be like 128 bit or it can be 1024 bit. But picks some random number and sends it to her. If she has the shared key, she would use the key to encrypt that number. Send it back to Bob. And she also sends her challenge because she needs to verify that this really is Bob and not somebody else who's trying to establish a secure channel with her. So if this really is Bob, then and if they share the key, he would be able to decrypt this and see that this is the same random number that he sent to her. Same situation with Alice. When she gets the response back from Bob, it's encrypted with a shared key. And she can decrypt it using the same key, because it's a symmetric key, and obtain back her random number. So, this algorithm, the way we see it, this is called two-way authentication using challenge response protocol. So the way we see it, it takes 5 steps. We could do the same thing in 3 steps. The first, to do that, Alice will send her identity and her challenge in the same request. And Bob would send his random number and encrypt her challenge in his response. And the final step would be that Alice would encrypt his challenge and send it back to him. Now, this kind of algorithm can have some issues. Can you think of a way that this can be compromised by Trudy? So Trudy is the intruder. Trudy is the third party that is sitting on the network and is listening. She can intercept messages, any of these messages. So she can copy them, read them. She can try to respond back to either Alice or Bob with some stuff that she sends. Do you think this algorithm is okay, or do you think it can be broken somehow?
Well, if you have more than one session, you can use that to get the answer. You make them get their own answer back.
Okay, so excellent. So what he's saying is that this is a single session of communication between Alice and Bob, but Trudy can open a second session, and in the second session, Bob will send to her the key because he would encrypt his challenge with the key. And so once she gets that key, she can respond to him from the communication in the first session and complete the process. So this is called a reflection reflection attack. So the way we have seen this algorithm, it's vulnerable to reflection attack. Now, we can try to secure the algorithm from this reflection attack, and we have a way to do that. We can have initiator prove who they are before the responder does that. It would avoid the issue that's currently happening. We could have the initiator and responder use different keys, which will be similar to the idea of a public and private key, instead of using symmetric key. We can have them draw challenges from a different set of keys. Now, whatever we do in this situation, we need to somehow have Alice and Bob agree on a shared key. We said that we have the key AB, which is shared between Alice and Bob. We have assumed so far that this key is a piece of information that both of them have already and that they have agreed upon, and then we've based our protocol on that. So how can they agree on a key? I mean, think about it. Trudy is sitting on the network. She can intercept network packets. She can't intercept this private key because it never really goes through the network. But anything that goes through the network, she can't copy. So if two people are to communicate with this shared key, then they need to somehow agree on the key. One way to do that is, for example, to call on the phone. Call on the phone and talk to each other and agree on the key. Another way is to meet in person, maybe, to avoid the network, and show each other's passports and driver's licenses to verify that this really is the person that we're talking to, and then agree on a key. But if this is to be done through a network, what can we do? Is anyone here from group 9? You guys that were presenting last time? They talked about this algorithm, which is almost powerbound. So these two scientists called Diffie and Hellman, these guys, mathematicians, came up with a brilliant mathematical formula which allows us to securely establish a shared key between two total strangers. So the way this works is by exploiting the property of modular arithmetic, which is pretty much a one-way function. The one-way function that I described here, it's easy to encrypt and go on direction, but it's hard to reverse it. And so this modular arithmetic is used in secure systems a lot. The other thing is that it uses prime numbers, because prime numbers are also easy in one direction and hard in the reverse direction. So the way this works, and we went over it quickly during the presentation last time, but Alice and Bob would agree on two numbers which are public. The numbers, we call them N and G. They are public, which means a Trudy can copy them, and then, for example, Alice can pick them and send them through the network. From these two numbers, N is a prime number. Another property is that to make this work mathematically, N minus 1 divided by 2 also has to be prime. So that's the first thing. We need these two numbers. Next, we have another two numbers which are private, X and Y. So Alice picks a large number. A large means at least 1024 bits. And this number is called X, and this number is private. She keeps it private. Bob does the same thing, so he picks his large private number. So for Alice's X, for Bob is Y. And from there on, we have what is shown on the slide. The first thing is these two numbers, N and G, are public, so Alice picks them and sends them publicly. Then she calculates a function called modulus n, g to the power of x modulus n, and sends this to Bob. What Bob does is the same thing, but instead of raising to the power of x, which x is the private number for Alice, he raises to the power of y, which is his private number, and sends the result to Alice. Now, once Bob has this piece of information, g to the power of x, and Alice has g to the power of y, what they do is they compute g to the power of x times y modulus n. So when they compute that, they do it by using this formula, g to the power of y modulus n to the power of x, g to the power of x modulus n to the power of y. In both of them give the same result. G to the power of x times y, or g to the power of y times x, is the same thing. So when they do this computation, they end up with the same result. And this was the nifty, elegant formula that those two scientists discovered. Once we apply this formula, both of them end up with the same result, with the same number. The number is g to the power of x times y modulus n. And so when they up with the same number, they have a shared secret key. But Trudy cannot intercept that because she doesn't have, because the one number X is private to Alice and the other number Y is private to Bob. But you need both of them in order to arrive at the shared key. And the last time we have seen a video of this. So I'm going to go just very